Understanding the structure of the atomic nucleus has posed a challenge since Rutherford's discovery. The nucleus is impenetrable. So how to explore it? Research has advanced significantly with the discovery of the constituents of the nucleus, protons and neutrons. Protons carry a positive charge, while neutrons are neutral. Their masses are nearly identical. Being essential components of a nucleus, they are collectively referred to as nucleons. Protons and neutrons are not elementary particles. Such a conclusion was initially reached theoretically, but in the 1960s the presence of smaller particles was proved experimentally, leading to the discovery of quarks. 3 quarks, but not 3 of the same kind, make up each nucleon. A proton is made up of 2 up quarks and 1 down quark. A neutron is made up of 2 down quarks and 1 up quark. The charges of the up and down quarks differ despite their many similarities. The charge of the up quark is plus 2/3 of the elementary charge. The charge of the down quark is minus 1/3 of the elementary charge. A straightforward summation of the charge carried by quarks results in the total charge of nucleons. For the proton, it is plus 1 elementary charge. For the neutron, the total charge is 0. There are other quarks besides the up and down quarks, but they have no bearing on the structure of the atomic nucleus. The tremendously intense force holds quarks together inside nucleons. This force is referred to as the strong nuclear force. It is so powerful that any attempt to separate the 2 quarks would result in the transformation of energy into mass. A new pair of quarks would be created. Quarks cannot exist in nature as free particles. The role of a strong nuclear force does not end here. It also holds all the nucleons within the nucleus. Because the strong nuclear interaction only exists between quarks, nucleons will attract each other only when they are close enough. A strong nuclear force has a very limited range. Another force, caused by the positive charge of the protons in the nucleus, is the repulsive Coulomb force. Since the Coulomb force decreases with the square of a distance, every proton in the nucleus repels every other proton in nucleus regardless of its location. Therefore, the nucleus has 2 opposing forces. The Coulomb force tries to disintegrate the nucleus. The strong nuclear force holds the nucleons together and keeps the nucleus whole. The number of protons in the nucleus identifies the chemical element. In our case, the nucleus contains 7 protons. A quick look at the periodic table of elements reveals that it is nitrogen, denoted by the letter N. The number of protons, represented by the letter Z, is the element's atomic number and is written next to the chemical symbol below. The mass number of nuclei is the total of the number of protons and neutrons in the nucleus. It is represented by the letter A, which appears above the atomic number. The number of neutrons in a nucleus is not necessarily constant. This does not suggest that neutrons can freely enter or exit the nucleus, but rather that a specific chemical element is represented in nature by multiple variants. All of them have the same number of protons, but have a different number of neutrons, and thus a different mass number A. Isotopes are variations of a single chemical element having different mass numbers. Two nitrogen isotopes, N14 and N15, are found at the same place on the periodic table of elements. Literally, isotope means the same place. However, N14 is far more common than nitrogen N15 in nature. Since an element's chemistry is defined by its electronic structure rather than by the contents of its nucleus, isotopes share the same chemical properties. They can, however, differ greatly in terms of nuclear properties. Something special occurs when an atom's nucleus is formed. Something that isn't observable in everyday life. The mass of the nucleus that these nucleons create is less than the sum of the masses of the individual nucleons. This seems to contradict the law of conservation of mass. But no. Due to the immense binding energy among nucleons in the nucleus, some of the mass of free nucleons must have been used to form these bonds. Each nucleon gave up a portion of its own mass, which, in accordance with Einstein's formula, became the energy that bound one nucleon to the other. We refer to this phenomenon as the mass defect. The graph displays the average binding energy of all known isotopes. Stable isotopes are denoted by black dots and unstable isotopes by red dots. Lead-208 appears to be the last stable isotope. The isotopes that follow are naturally unstable and prone to decay due to their large nucleus. They are radioactive. The most stable isotope of any chemical element is the one with the highest mean binding energy. The black dots are always above the red dots. Research indicates that nuclei with a specific number of nucleons, known as the magic numbers, are most stable and have greater binding energies. By analogy with the electron configuration, the existence of exceptionally stable nuclei implies that nucleus has energy levels that are occupied by nucleons. The nucleus is most stable when the energy level is filled. In the same way, the noble gases have fully occupied electron energy levels, which makes them exceptionally chemically stable. This nucleus model is known as the shell model of the atomic nucleus.